Aloha! Welcome to Data Frontiers. Degree of freedom, DF, is an intimate stranger to statistics students. Almost every quantitative-based research paper requires reporting of degrees of freedom associated with the test results, yet very few people understand why it is essential to do so. Many statistics textbooks introduce the concept of degrees of freedom in terms of the number scores that are free to vary. However, this explanation cannot clearly show the purpose of DF. There are many other approaches to present the concept of degrees of freedom. Two of the most meaningful ways are to illustrate DF in terms of sample size and dimensionality. Both represent the number of pieces of useful information. My statistics professor Larry Toothaker explained DF as the number of independent components minus the number of parameters estimated. This approach is based upon the definition provided by Helen Walker: the number of observations minus the number of necessary relations, DF equals to n minus r. Although I.J. Good criticized that Walker's approach is not obvious in the meaning of necessary relations, the number of necessary relationships is indeed intuitive when there are just a few variables. Necessary relationship can be defined as the relationship between a dependent variable, y, and each independent variable, x, in research. Please note that this illustration is simplified for conceptual clarity. Although Walker regards the preceding equation as a universal rule, DF equals to n minus r might not be applicable to all situations. This figure shows that there is one relationship under investigation, the number of r is 1, when there are two variables, x and y. In the scatter plot, there is only one datum point. The analyst cannot do any meaningful estimation of the regression line because the line can go in any direction, as shown in the figure. Line A, B, C, and D are equally valid or invalid. In other words, there isn't any useful information. When the degree of freedom is 0, df equals to n minus r equals to 1 minus 1 equals to 0, it is impossible to affirm or reject the model. In this sense, the data have no freedom to vary. Bluntly stated, one subject is basically useless, and obviously, DF defines the effective sample size. The effective sample size is smaller than the actual sample size when DF is taken into account. In order to plot a regression line, one must have at least two data points as indicated in this figure. In this case, there is one degree of freedom for estimation, n minus 1 equals to 1, where n equals to 2. When there are two data points only, one can always join them to be a straight regression line and get a perfect correlation, r equals to 1 or 100%. This perfect fit results from the lack of useful information. Since the data do not have much freedom to vary, no alternate models could be explored. Indeed, a perfect relationship is too good to be true. There are no Snow White and Prince Charming in reality. Perfect models are often flawed. True models involve imperfections, fostering realistic and reliable statistical practices. In addition, when there are too many variables in a regression model, that is, the number of parameters to be estimated is larger than the number of observations, this model is said to lacking degrees of freedom and thus is overfit. Conceptually speaking, there should be 4 or more variables and 3 or fewer observations to make a model overfitting. Nevertheless, when only 3 subjects are used to estimate the strength of association between 2 variables, the situation is bad enough. Since there are just a few observations, the residuals are small, and it gives an illusion that the model and the data fit each other very well. When the sample size is larger and data points scatter around the plot, the residuals are higher, of course. In this case, the model tends to have a lower degree of fit. Nevertheless, a less fitted model resulted from more degrees of freedom carry more merits. In the case of perfect fitting, the model is always right. In overfitting, the model tends to be almost right. Both models have a low degree of falsifiability. The concept, falsifiability, was introduced by Karl Popper, a prominent philosopher of science. According to Popper, the validity of knowledge is tied to the probability of falsification. Scientific propositions can be falsified empirically. On the other hand, unscientific claims are always right and cannot be falsified at all. We cannot conclusively affirm a hypothesis, but we can conclusively negate it. The more specific a theory is, the higher possibility that the statement can be negated. When there is no or low degree of freedom, the data could be fit with any theory, and thus the theory is said to be unfalsifiable. Next, degrees of freedom are illustrated in terms of dimensionality and parameters. According to I.J. Good, degrees of freedom can be expressed as dk minus dh. dk is the dimensionality of a broader hypothesis, such as a full model in regression. dh is the dimensionality of the null hypothesis, such as a restricted or null model. In this figure, vectors in hyperspace that represent variables are used for illustrating a regression model. It is important to point out that the illustration is only a metaphor to make comprehension easier. Vectors do not behave literally as shown. In hyperspace, vector y represents the dimension of the outcome variable, whereas vector x1 beta 1 and x2 beta 2 denote the dimensions of the predictors with two estimated parameters. Vector y hat is the dimension of y expected. In this example, the intercept is ignored. In a null model, the number of parameters is set to 0. The expected y-score is equal to the mean of y, and there is no beta weight to be estimated. What is the degree of freedom when there is one variable, vector, in a regression model? Since only one predictor is present, there is only one beta weight to be estimated. Based upon df equals to dk minus dh, when there is only one predictor, the degree of freedom is just 1. 1 minus 0 equals to 1. It means that there is only one piece of useful information for estimation. In this case, the model is not well supported. As you notice, a two-predictor model, df equals to 2 minus 0 equals to 2, is better supported than the one-predictor model, df equals to 1 minus 0 equals to 1. When the number of orthogonal vectors increases, we have more pieces of independent information to predict y, and the model tends to be more stable. In short, the degree of freedom can be defined in the context of dimensionality, which conveys the amount of useful information. However, it is important to note that some regression methods, such as ridge regression, linear smoothers, and smoothing splines, are not based on least squares, and so df defined in terms of dimensionality is not applicable to these modeling methods. The above illustrations, Walker's df and Good's df, compartmentalize df in terms of sample size and df in terms of dimensionality, variables. However, observations, n, and parameters, k, in the context of df, must be taken into consideration together. For instance, in regression, the working definition of degrees of freedom involves the information of both observations and dimensionality. df equals to n minus k minus 1, whereas n equals to sample size and k equals to the number of predictor variables. Take the 3-observation and 2-variable case as an example. In this case, df equals to 3 minus 2 minus 1 equals to 0. The above explanation is illustrated in the context of regression modeling. In the context of structural equation modeling, SEM, and confirmatory factor analysis, CFA, df is an indicator of whether the model is identifiable or testable. In this context, df is calculated as the number of distinct elements in the covariance matrix minus the number of free parameters to be estimated. It is similar to Walker's approach, but at the time of Walker's writing, structural equation modeling had not been introduced yet, and thus Walker did not incorporate the covariance matrix into the equation. This figure shows a simple structural equation model carrying 5 variables, p. In this model, the number of distinct elements is p times p plus 1 divided by 2, which is equal to 5 times 6 divided by 2. The answer is 15. There are 4 path coefficients, a to d, b to d, c to d, and d to e, symbolized by the single-headed arrow from a to e in the diagram, and 5 variances, a, b, c, d, and e, symbolized by the double-headed arrow in each rectangle. Additionally, there are 3 pairs of covariance among the variables. Taking all of the above into account, the number of parameters is 12, and thus the df is 15 minus 12 equals to 3. However, if the number of parameters to be estimated is more than the number of distinct elements, or the two are equal, the df becomes negative or 0, and thus the model becomes untestable or falsifiable. Specifically, you need at least 3 observed items for a latent factor. If there are 2 items only, then there will be 3 distinct elements, sample moments, and 4 parameters to be estimated. As a result, df equals to 3 minus 4 equals to -1. The model is untestable or unfalsifiable. Traditional statistics prioritize df, while modern techniques like machine learning de-emphasize it due to robust methodologies. For example, if a data set has 20 observations only, but there are 21 potential regressors, then the regression model is invalid due to losing degrees of freedom, p larger than n. However, it is not a challenge to DSML. For instance, in a study about detecting early microarray lymphoma, there are 81 cases and 4,682 variables. By using the random forest, one of the powerful DSML methods, the error rate of the model is just 1.23%. Although you can still calculate df using p and n, the importance of df has been diminishing since the dawn of DSML. In summary, degree of freedom can be understood in the context of sample size and dimensionality. In the context of sample size, df equal to n minus r. When n is too small, the model will suffer from perfect fitting or overfitting. In this case, the model is untestable or unfalsifiable. In the context of dimensionality, df equal to dk minus dh. When the number of orthogonal or independent vectors increase, the variance tends to be better explained, and the model tends to be more stable. In both senses, the degrees of freedom tells us the number of pieces of useful information. In research, both should be taken into consideration in determining whether there is sufficient formation. An example of integrating both can be found in regression, which is df equals to n minus k minus 1. In the context of confirmatory factor analysis and structural equation modeling, df is an indicator of whether the model is identifiable or testable. df is calculated as the number of distinct elements minus the number of free parameters to be estimated. If the model is highly misspecified, meaning that there isn't sufficient information, then the degrees of freedom could be negative. In the era of data science and machine learning, df becomes less and less important. As you might already notice, df is not reported in many DSML results. Most DSML procedures can still function, even if the number of variables is far greater than the sample size. I hope this clarification is helpful, and from now on, df is no longer an intimate stranger to you. Thank you for watching.